Okay, so if we make caches bigger and bigger and bigger, the chances of contention go down because we have many more cache lines to map the addresses. And so what we hope is that by spreading out we're going to spread out the information over a larger cache, and so the chances of any two things colliding get somewhat smaller. So we'll discover that we'll want to build large caches, and that's always a good first step. Given a choice about what architectural parameter to adjust in the cache, consider making it larger. That's always a good thing. And in fact, I'm going to pull a number off my head. 80–90% of the transistors you buy from Intel are transistors devoted to big caches. And then you happen to buy a little CPU. But the reason that, it doesn't make any sense to have a CPU that can execute instructions a bazillion times faster than the cache and memory system can deliver them on the average. So it's getting that ratio right that you pay for when you buy many cache transistors. Okay, remember this diagram here when we were talking about locality of reference, and we sort of identified we're fetching program, some information from a program, and there's a lot of locality there. We're fetching information from a stack frame. We're perhaps dealing with data structures or pieces of arrays here. If we think about how many different hotspots there are, there's not an arbitrary number of them. It turns out there's only 3 or 4 or 8 or 6 or something, but a handful of hotspots that over several hundred instructions that most programs will be accessing. They'll be accessing the hotspots a lot of accesses to the stack frame, a lot of accesses to the instruction in the loop. But there's only, and if each one of these can be located at a different place in memory, they have the possibility of colliding. But there's only, in a sense, sort of 5 or 6 collision possibilities that we have to deal with here, right? Because we have to worry about the data colliding with the stack, colliding with the program. But those there's a certain locality and coherency to each of those separate address regions. And so what we're going to do is design our cache to take advantage of this small number of hotspots. Okay, instead of having a direct map cache, we like the direct map cache because they're sort of simple. What we're going to do is to make a collection of n direct map caches. Okay, so instead of having a single location at which a particular address can be cached, we're going to have a set of locations. One element of the set comes from each of the n caches. So these things are called n-way set associative caches. Okay, so they look like this. And I hope you can certainly realize that this is just a picture of a direct map cache. But instead of having a fully associative cache, which you can think of as a single line, we're going to have a fairly substantial direct map cache, but we're going to have n copies. And one of the things we need to talk about, what should n be? 2, 4, 8, 32, 128? I mean, what's the right number? Okay, so let's talk a little bit about that. But everybody just sort of see this picture here. These are n, and the picture here shows 3 almost. And although there's no particular reason that there should be a power of 2, they almost always are a power of 2. So 2 or 4 or 8-way caches. These are n direct map caches operating in parallel. They're each checking to see whether that particular cache line, the one that's indexed by the lower order address, happens to hold the contents of this of the memory location the CPU is trying to access. So here's some questions. Is it possible for a location to be nowhere in the cache? Of course. I mean, the memory system hasn't loaded it. Okay. We expect it to be, hopefully it will be in one location in the cache. In a system like this, would you ever expect to find a memory location cached in more than one of the direct map subcaches? In other words, could a particular memory location appear more than once? Well, there's 2 ways to answer that. One is it would be sort of silly. It would be a waste of resources if it appeared more than once. It's a little unclear what this hardware would do. Okay, if they said, this guy said, I have a hit and turned on his drivers for his data line, and this guy says, I have a hit and turned on his drivers. It would be even worse if they sort of were remembering different values, right? So in general, all caches are designed to hold each location 0 times or 1 time, but not more than 1 time. So the goal will be to actually have this act like a very big cache. In other words, this particular guy can have, well, I'll just literally look at this picture, 3 times n locations, or 3 is n, excuse me, 3 times 2 to the t locations in the cache. So it has a lot of locations. It's just divided up so that we're using the direct map technology to figure out where to look. Everybody sort of get that? This is not a complicated picture. Yes, sir?
Just to make sure, each yellow thing is direct map cache.
Each one of these columns is a direct map cache.
So the T word lines go to each of them in parallel.
So we're doing, in this case, n possible searches in parallel. We're not searching the entire cache in parallel. We're searching n where n is 2 or 4 or 8, depending on the number of direct map caches we're doing. So we're getting some amount of parallel search. And what we're going to find when we look at some performance graphs is by the time we get to about an 8-way set associative cache, it's as good as a fully associative cache almost always. Okay, so the terminology, just to be clear, is that a cache line is in a particular one of these direct map caches. It has a tag and some data. And then there's a set of cache lines where each element of the set is coming from a different direct map cache. So when I talk about a set associative cache, the set I'm referring to is the set of locations that a particular address can appear in. And it will appear in at most one of them. Okay, so the numerology of caches, you should sort of look at this slide and sort of figure it out, right? I mean, what would it mean to be a fully associative cache? I mean, that's like setting t to 0. What would it be like to be a direct map cache? That's like setting n to 1, so forth and so on. So the entire space of cache architectures are sort of described, along these axes, and exactly which place along these 2 axes you should choose. This is now we're back to figuring out, on the average, we want our machine to perform well. Okay, so what we need to do is to spend a little bit of time thinking about how to perform well. Okay, so the first thing I want to talk about here now is if I have an associative, so in both the n-way set associative and the fully associative caches, okay, I know there's a slide coming, and I'm just making sure I knew where it was. Okay, so in an n-way set associative cache or in a fully associative cache, we do have this problem where once something is, I need to bring a new thing into a cache and I need to replace something else. How do I make that choice? Okay, so we have a replacement strategy issue, so we'll talk briefly about that.